we're going to let f of x equals the square root of 1 minus x squared. And we're going to have the points a, which is at negative 1, comma f of negative 1, and b, 1, comma f of 1. And I want to determine the tangent line in the interval negative 1 to 1 that is parallel to the line formed by intersecting a and b. So the reason that the negative 1 and the 1 are in an open interval is because that's what I need to be differentiating towards. So let's go ahead and take a look at this graph and see what it looks like from the interval negative 1, f of negative 1, and 1 to 1. So if I bring up the graph, here it is. This is the graph of the square root of 1 minus x squared. And you can see its domain is actually just negative 1 to 1. So what I'm going to do here is I'm going to go ahead and put this into our notes. So I recommend you take a moment and draw this. Because what we're going to need to do right now is determine if the mean value theorem even holds. The reason we want to use the mean value theorem is because this right here. We want to find a tangent line that is parallel. Well, that's the mean value theorem. The mean value theorem says that if everything holds, then we are guaranteed to get a tangent line that is parallel to that secant line. So we have to check, does the MVT apply? Well, let's check our criteria. So f is continuous on a closed interval, which is negative 1 to 1. But here's the thing. F is not differentiable on negative 1 to 1. Because right here, we don't have a right-hand derivative. We don't have this. And right here, we don't have a left-hand derivative. But that's okay. And the reason it's okay, because the mean value theorem says that f has to be differentiable on an open interval. And so I'm going to choose my open interval to be negative 1 to 1, and now my function is actually differentiable. So the trick here is we're not going to include these endpoints. So we're modifying what we're trying to get. Now, is it okay that we modify the problem? It is. And the reason is the parallel line is not going to be at those points. So for example, this is where I'm making my domain, and I'm cutting it off and saying that I'm not going to worry about this point and I'm not going to worry about this point because I don't think that my tangent line needs to be like this steep. That's my point I'm making. But let's see if it does. So what we're going to do is we're going to go ahead and go back to the graph, and I'm going to graph the line that intersects A and B. And so that's right here. That's this purple line right here. It goes through A and B. So I can see it needs to be a horizontal line. So my tangent line then is going to look something like this. Well, I can see right here that this is not parallel, not even close. And as I move around, I can start to see it become more and more parallel. And as I go here, it's not parallel, but as I continue, it's probably somewhere close to right about here. But right here, I'm using the 0.01. I'm not at 1, but it looks pretty parallel. But if I move it to here, it looks more parallel, or actually parallel. And so we need to actually determine the value at which these make a parallel line, because this kind of looks parallel, but it's not. So to do that, what we're going to do is we are going to use the mean value theorem. And the mean value theorem says, and this is the mean value theorem right here, it says that f prime of c, the derivative at a point, is equal to the average rate of change. The derivative of a point is equal to the average rate of change. Well, let's just start plugging in some values what we know. We're going to go ahead and we're going to solve for this piece right here right now. And so in this, I need to know f of b, I need to know f of a, I need to know a, and I need to know b. So a in this case is -1. B in this case is 1. So f of 1 is going to be 0. And we can see that right from the graph, or you can just plug it into your equation. F of -1 is also 0. Again, by plugging it into the equation or just looking at the graph. So then f prime of c is equal to 0 minus 0 divided by 1 minus a -1, which is 0 over 2, which is 0. As you can see from the tangent line right here, or not the tangent line, the secant line right here, this is the equation y equals 0, which also has a slope of 0. So given that, we're going to go ahead and we're going to find a value such that works. So I need to find f prime of c and set that equal to 0. Well, I need to know what f prime is first. So I know f of x is equal to the square root of 1 minus x squared, which I'm going to go ahead and rewrite as 1 minus x squared to the power of 1/2. So I take the derivative of that, and I get f prime of x is equal to 1/2 1 minus x squared to the -1/2 times a -2x. So I get -2x divided by 2, 1 minus x squared to the power of 1/2, which gives me x divided by 1 minus x squared to the power of 1/2. So f prime of c then is equal to c divided by 1 minus x squared to the power of 1/2, and I'm going to set that equal to 0. And whenever you want to solve for a rational function, you just set the numerator equal to the 0. And so from there, you're going to get that c is equal to 0. So that's good. That's the x value such that the derivative is equal to 0. And so what this means is that the slope of the tangent line is 0. Our conclusion then is that y equals 1 is the tangent line to f and parallel to the line AB. And where in the world did this y equals 1 comes from? Where this y equals 1 came from is I noticed that this c value is 0. So what I do then is that's my x value. So what I do is I go ahead and look on my graph. My x value is 0. So this point on my graph right here is 0, 1. That means that the tangent line is right here. In this example, we're going to try to determine a couple things. So we're going to determine the same thing as the last example, however, a little more structured. You can follow these steps if you want to prove the mean value theorem holds, or find if it's a particular value where the tangent line is a certain slope. So we're going to take f of x equals x plus 1 over x from the values 1/2 to 2. And we're going to first determine the secant line of the line that joins AB and the tangent line that is also parallel to that secant line. So the very first thing I want to do is I want to look at what this graph looks like. You don't necessarily need to graph it to solve this, but I want to go ahead and show you what this looks like. So this is what we're dealing with right here. This is what the graph looks like. And if I was to join AB, I get this line right here. Now you can see this is a pretty horizontal line, so then the parallel line that I'm going to want is going to be equal to 0 for the slope. So, but we're going to use algebra to actually make sure this is exactly 0 and not like 0.00001. But I'm just going to give you a little visual display of what's going on. As I move this point around, I can get a slope I can get a slope that moves around like this. And as I move this point around, you can see how the slope will change. And so ideally, I'm going to probably want to be here at 1, but we're going to prove it algebraically and show what is actually going on. So here we go. There's a couple things we're going to need, but we'll figure those out as we go. There's a couple things we're going to need, and we will figure out those pieces as we go. So we want to determine the secant line. And so to determine the secant line, we need to find its slope, and slope is f of b minus f of a divided by b minus a. So keep in mind that this is our a value, this is our b value. So then f of b is going to be f of 2, which is 2 plus 1/2, which is equal to 5/2. F of a is then f of 1/2, which is 1/2 plus 1 divided by 1/2. So this becomes 1/2 plus 2, which is also 5/2. So now you just plug this in our formula, and we get 5/2 minus 5/2 divided by 2 minus 1/2. So you get 0 divided by 1.5, which is 0. Now, I didn't actually need to determine the actual equation for the secant line. What was more important was the slope. So when this is saying determine the secant line, we're really talking about the slope of that secant line. So I'm trying to find the tangent line that is parallel to this line AB. And so what I really want is a line that's tangent to the curve but also has a slope of 0. So to do that, I'm going to take f of x, which is x plus 1 over x, and I'm going to find the derivative, because that's how you find slope of a tangent line. So this is 1 minus 1 over x squared. And I'm going to go ahead and I'm going to set that equal to 0 because that's the slope I want. I'm going to do a little solving, and you get x is equal to plus or minus 1. Well, this means I get two answers. I get x equals 1 and x equals negative 1. Well, that's all fine and dandy, except remember our domain is 1/2 to 2. So this value's not going to work. So what I need to do is I need to find the slope at a point. So what we want to do now is plug the 1 value into our original function to find the y value that goes with it. So f of 1 is 1 plus 1 divided by 1, which is 2. So it gives us the coordinate 1, 2. This is our x and our y value, and we know our slope is 0. So what we do from there is we're going to take all our components to find the equation of a line. Y minus y1 is equal to m times x minus x1. You get y minus 2 is equal to 0 times x minus 1. So y minus 2 equals 0. And from there you get y equals 2. And this is the equation of our tangent line. And to just confirm that, let's look at the graph. Well, if I look at the tangent line, if I look at the line right here, you can see these tangent lines are parallel, and this is y equals 2.